Welcome back, folks. So we're a part two of testing out this XDM2041 from OWON. And we've got quite a bit to go through today, so I'm going to get started pretty quickly. One thing that I forgot to mention in the last part of it, the voltage reference in this thing is a Max 6071 series. And the resistor network in it is just surface mount resistors. There are 6 of them. 4 of them are 0.1% resistors and 2 of them are 1% resistors. And you might think, well, how can they get that kind of precision, the precision that they're claiming here, with those resistor values? Well, they can because the DMM component in it, the analog component in it, does have a calibration. You can calibrate each one of the switch inputs whichever way it needs to be calibrated, so they can get by with relatively inexpensive resistors and still get fairly precise results. And we'll check that out. So what I'm going to do with the testing here is I'm just going to first start out with things that I can't bring in the other multimeter because, you know, ohms and capacitance and stuff like that. You can't parallel meters or put them in series. So we'll look at the ohms first. So what I'm going to do is I'm going to get my little box here. Now this box has been checked out with my Siglent SDM3055. So it's a 5.5 digit meter, more precise than this one is, but we'll test this one out anyway. So let's start off here at the 10 megohm range. So I saw on the internet some people were having trouble in this range. They're saying that the readings were bouncing around all over the place in the 50 megohm range. I'm not seeing that here. There's a little bit of a bouncing around, but not much. It's within the precision of the meter. Let's go down the list here. So we'll go down to 100K here. Yeah, it's 99.91, so it's within accuracy, as is this, and so is this. Down to 100 ohms. That works out too. And that's a 1.053 ohm resistor, and that's fine as well. That's perfectly within stated accuracy. So it looks like those resistor dividers that they put in there are fairly well adjusted, or fairly well calibrated. Okay, let's take a very quick look here at the 4-wire mode. So we put that in 4-wire here, and we get that 1 ohm resistor that we had before. We'll check it out in 4-wire mode and see what it comes up as. He's in there nicely. Okay, here. So see, it comes up around about 1.03 ohms, and that's about a 0.03 ohm discrepancy, maybe 0.025 ohm from what we read before. And what that is caused by is just the length of the leads. This using 4-wire, because the voltage and the current are measured independently, it takes the resistance of the leads completely out of the circuit. And I can show you that with the rel mode. So we'll put this back into 2-wire mode. Get a couple of wires in here and put them into our resistor box here. And we can see we're back to the reading that we had before. Go directly in. Now let's see what the rel mode can do for us here. Let's get these two here, kind of short them out. And then we press rel. And let's go back to our box here and measure that. And now you see that we're coming up with 1.03. Let's move on here to diodes. So what I wanted to do first, before we test the diodes themselves, is to actually check to see what kind of voltage it uses to check diodes with. So anything over 3 volts would be nice. And we have, 3.28, that's good. That's fine. All right, let's check those diodes, and then I want to check the current that it puts through them. All right, here, so there we're only 0.36 milliamps. So I imagine it's going to read all these diodes pretty low, because that's not a lot of current to put through them. But it's safe in a way. It's not going to damage a very, very sensitive diode. Okay, let's continue on with the rest of the measurements. So 0.2165, we expect this one to be a bit low too, 0.5538, but definitely in the ballpark. You're going to get a very good idea of what your forward voltage is on these. I mean, you could build a special test rig that would test the forward voltage under different currents, and you might want to do that for certain reasons, but just to get a quick idea of what board voltages with 0.3 milliamps going through it. There, you've got it there. So it's doing that just fine. That's perfect. Okay, let's what's the continuity like here? Put the beeper on. So it gives the reading in ohms too. So if we get this back here again, we can see that it'll give us the approximate reading in ohm of the continuity. Now if we go up here, we can change the threshold here. So if we go over here and change the threshold to 150 ohms, and then we try this 100 ohm resistor, it should detect it and tell us the resistance. So that is pretty neat. Very good. So that works well. It's got a nice loud beep, and it seems to be latched as well. So all right, let's now move on to capacitance. I don't think these meters are really good at measuring capacitance. Before we measure the capacitance though, let's look at the signal at which it's measuring the capacitance with. So let me hook up a scope here, and what we're going to try and do is, you see that oscilloscope up there, we're going to try and see what the signal is that it's using to value capacitors, and it is about 230 millivolt peak to peak. It looks like a capacitor charge and discharge, and it is at about 23.27 kilohertz. Now that's probably going to change if you put a capacitor across there. Let's have a look to see if we can see that while it's happening. So we're now down about 362 hertz. And that's how it does the calculation. So it just reads the frequency and calculates the capacitance from there. Let's see if we bring it down to 540 PF. Good enough. So let's keep on going up along the list here. 19.25, that's close enough. 470, 480. I'm going to say that's close enough. I mean, you don't really use a meter like this for working out capacitance. You use an LCR meter of some kind, even one of those little component tester devices. And it's got that one right, but it's got it right. Yeah, so it's fine in capacitors. So now let's try temperature. I'll go get a thermocouple, and we'll put it off the temperature here. So the internal temperature of the thing is 21.7 degrees, which is supposed to represent the cold junction temperature of the thermocouple that I'm going to plug into it right now. So I've got to get the polarity right here, and that should go in like that. It's reading about 19.8. That seems fair enough. This will be a little bit colder than the one in the box here. Let's compare it to the Siglant. Hold on. Okay, we got that Siglant up on temperature, and it seems to be awfully confused about what the internal temperature is. But let's plug this in and see what it comes up with compared to the. So it's measuring 22 degrees, and this was measuring 19.8. I don't know which one is the most accurate. Let's take out a third meter and use it as a tiebreaker. So we'll use this one here. This one says 14.5 degrees. So we're all over the map here with temperatures. You know, I would say that the Siglant and this are the closest, so they're within a couple of degrees of each other. That's fine. All right, now frequency. Let me set up for that, and I'll come right back. Okay, we've got the function generator hooked up to both this and to the Siglant, and we've got the both in frequency mode. Now this one says that that for frequencies below 10 megahertz, the applicable voltage should be over 1 volt AC, and when the frequency is over 10 megahertz, it should be 3 volts AC. So we'll start off here with 2 volts, and we'll enable it right now. So output on, and okay, we're getting 999.97, and the Siglant is showing exactly 1 kilohertz. That's well within the specifications, which are, yeah, plus or minus 0.2% and 8 counts. So yeah, it's perfect. So let's try 10 kilohertz. let's go up a little bit. Let's put in 1 megahertz. So 999.97 kilohertz, and the signal says 1 megahertz. Let's go up to 10 megahertz. So 9.9997 megahertz. So it looks like the crystal reference in here is off just by a smidge. The signal has died away on us. It's not able to do this. We're stuck here at 2.12 volts, which is the most that my generator can do. And this is doing fine, but the signal has dropped out. So let's go up to 20 megahertz then. I don't know if this will be all because I can't get up to the 3 volts, but it's doing fine. It's up to 20 megahertz. I expect we'll drop out here because we can't get up over the 3 volts required. Let's see where it does drop out. Let's go up to 30 megahertz. Yeah, it's dropped out there. Let's bring it back down a little bit at a time. Try 25 megahertz. It's okay with 25 megahertz, 26 megahertz, 27, and that's it. It won't do 28 megahertz properly. But it's doing better than the Siglent. Considering we can't give it the voltage level that it requires, we'll have to end the test here. But I'd say that's another pass. So far it's passed everything. Now we'll get into measuring things like the voltage and the current, and we'll compare that directly with the Siglent over here. Let me set up for that. I'll be right back. Okay, we'll test a voltage in each range. So we're down here at the lowest possible range of 50 millivolts, and we've got 26.11. It's matching pretty well exactly what the Siglent is doing as far as reading is concerned. Siglent's faster updating, but then again, it costs 3 times what this cost. So we'd expect a little bit better performance out of it. All right, so let me bring up the voltage now. The next range, let's have a look. Next range is 500 millivolt. Okay, let's get in the middle of that range there. And there, that's roughly the middle of that range. And we're at 225.9, and the Siglent is at 225.9. So yeah, it's right on there. In fact, we're showing the same number of digits of accuracy as the Siglent is at this particular range. So now let's go up to the 5 volt range. We get this thing up to about 2.5 volts. Okay, we're reading 2.5263 and reading 2.5268 on the Siglent. So it's keeping pace pretty good. It's well within its rated accuracy, absolutely. Okay, let's go up to the next range, which is the 50 volt range. So I've got to get 25 volts in there. Okay, it's reading 25.523, and the Siglent's at 25.527. Now the next range beyond that would be 500 volts. All right, we're up into the 500 volt range, but I could only manage 160.94, or according to the Siglent, 160.996. Within their respective specifications, they're both right on. Well, let's try some AC voltage. I can bring up the frequency generator again to get some low voltages. Then we can try the mains voltage. Okay, so here we are. I've got the signal generator putting out 2.121 volts RMS according to it. And the Siglent is reading it at 2.1254. This is reading it at 2.1258. And we have a dual mode. You can enable that or disable that, and it gives us the frequency as well. So that's a really nice feature. Let's bring it down a bit on the voltage here. Let's get down to the millivolts. It's still measuring the frequency. It's got 121.65 millivolts. So let's bring that down. So now we're down to 21.01. We're in the 500 millivolt range. Let's get down to 1 millivolt. It is not doing it. That is not great. Okay, so it's not going to be able to register anything below a certain level. So let's see, we're going to bring it up 2 millivolts, 3 millivolts, 4. Yeah, it'll do 5, but it won't do 4.9. All right, let's put some mains voltage on it and see what happens. We're measuring 122.73 on the OWON and 122.6. Now the Siglent's bouncing around quite a bit, about 1/10 of a volt difference, maybe a little bit less than 1/10 of a volt difference. Okay, so far it checks out okay, but I'm a little disappointed in it'll only measure down to 5 millivolts AC. All right, let's set up for measuring some current ranges. I have the power supply set at a 0.1 volts. It's going through this 100K resistor here, passing through both the meters. So I've got to set, according to the signal, I've got to set at about 1 microamp. And this is saying 1.07 microamps. And let's see what the tolerance is on that. It's 0.15% plus 20 counts. That's good. That's within specification right there. So let's, what ranges do we have here? 50 microamp, 5 milliamps. So let's get it up to 5 milliamps here. Okay, we're in the 5 milliamp scale here. We're reading 3.479, 3.476. So it's matching the signal there. The signal is bouncing around a little bit faster. Okay, let's go up. The next range up would be the 50 milliamp range. So we'll bring that up to 50 milliamps. Do 25. Get in the middle of the range. There we are, around 25 milliamps. 23.6 versus 23.6. So yeah, it's good there. Let's go with the next range up, which should be 500 milliamps. We'll put it up to 250. 253.21, 253.22 there, so it's right on. Okay, let's go up to 2.5 amps to get up into the next scale. Okay, 2.498, which is almost smack on. 2.4995 over on the Sigland. The most I can get is about 6 amps. It gets us up to the next range, but I can't get up to any higher than that. So let's try that 6 amp. Okay, it looks like about the best I can get here is 4.9 amps. So the beeping there is the power supply hitting current limit. And that's about all we can do for the DC amps. We'll set it up for AC amps and we'll come right back. Okay, here we are set up for AC current. I'm only going to test the bottom end of this scale. I don't really have a lot of useful tools for providing AC current around here. I think that the resistor network in here has proven itself through all the different ranges that we've seen. There's been very, very close agreement with the Sigland. So I can't imagine things are going to be a heck of a lot different with the AC. So we're going to start off down here with in the microamp range here. And we can see already that we have a little bit of a discrepancy as we did with the DC microamps. I'm reading a little bit higher over there on the signal than we are here on this. As we go down, can we get down lower than we did on the DC? So we're still good at 5 microamps, but then it drops out. So this meter is not capable of reading less than 5 microamps, either AC or DC. Let's bring it up a little bit more. See if we can get into the next range up anyway. Okay, we're in the 5 milliamp range. We've got 690 microamps going through it. Very good agreement there. We're in the 50 milliamp range now. We've got 8.54 milliamps. And a very good agreement with the Sigland again. That kind of finishes all my accuracy tests, and I think it passed everything. It should say in the specifications that it won't measure below 5 microamps, either AC or DC. It just says a resolution of 0.01 microamps, but it doesn't say that where it drops out. So it doesn't go down to 0. It doesn't go down below 5. If that's a concern for you, if you need to measure things in under 5 microamp range, this is not going to be the meter for you. So let's try and hook it up to the software and have a look at that. And I'll talk a little bit more of that in a minute. So overall, in trying to get the software up and running and connect it up to a PC, I found that the documentation is just a little bit scattered. Like nowhere in the quick guide or nowhere in the programming guide or nowhere in the user manual does it mention the pinout of the RS-232 port. It's a male connector, which is normally DTE. And so I went from the DTE on this to that using a crossover, or what they call a null modem cable. And of course things didn't work. And it wasn't until I decided, oh, well, I'll go ahead and install the software. Maybe it requires a special protocol, and maybe you can't use SEPI commands directly in text. And it was in that manual, the software install manual, that they do mention that the output on that connector is DCE, not DTE, even though it's a DTE or a male connector. Anyway, that's some of the joys of the whole RS-232 world, and that's why I wish they had put a USB interface on this. And you don't need a computer with an old-fashioned RS-232. This here is just a little USB to RS-232 dongle. This one's got a FTDI chip on it. But I'm sure that some of the CP or the CH340, 341s, those should all just work fine as long as Windows accepts the driver. They recommend XP version 7, version 10. I'm sure if it runs on version 10, it'll run on Windows version 11, so that's not an issue. Anyway, let's get it physically hooked up here. I've got this little USB here coming from the computer, and we'll get up the software on the screen. So this is called DMM Easy, and you have to go up to Control and click Connect, and then say via COM, and then pick the COM port. That's the COM port. It defaults to 15,200 baud, and click OK. And there we go. So we're reading what's on the screen right now, which is 41.30 milliamps DC, and I can turn that down as we were doing before, and switch down auto range, and we should get the reading again, 215.73. Now all the different things are available, so you can go over to DC volts, you go to AC volts, DC current, AC current. So they're all there. They're all available. The one thing that doesn't work is pressing run stop. Now it shows up here on the software that it has stopped the triggering, but over here you can see it hasn't, right? And that's the one way you get a hold feature is to stop the triggering. Now as far as recording goes, you can record directly to your PC. So if I here say save, it'll come up and ask me for a file to save to. So let's call this test.4. And then it asks you the parameters. So if you just go by default and go like this, it'll start recording as you go about doing your thing. So if you were to, change this here, DC current, because that's what we have going into the thing. And then we change that up and down. And then you just hit stop here. It should write the file out. And let's see if we can go and find that file. Text4, we've got 24 kilobytes of junk, but there it is. That's the format it comes in. So there's your file. You can record directly, like I say, to your PC, or if you have been taking measurements in here with the save button, you can save that too. And this is how that's done. So if you go up here again to record, go here to record, and then say device data export. So that'll go in and get that file internal in there. We call this TST5, and save that. This takes a minute or two for some reason, but it does save that file. It'll come up and tell you when it's done. I had recorded some data a little bit earlier in the day, and that's what the data was, and it allowed me to export that. It retains it after you power it down, power it back up again. So you can collect data over several different sessions and then export it out using this fancy software, which isn't all that fancy. That's the software. And I do believe I'm going to bring up this here to set up. 0 port, say, get it up to 115.200, new open. You want to enable local echo, and you want to receive cartridge return on line feed. Say OK. And there you go. So we're now connected up to it directly with a terminal here. So you could write scripts if you wanted to, or C programs if you're a real programmer, and extract data from it that way if you don't like to use their interface. And you could consult the programming manual for the different commands. For instance, like you could put in conf volt AC, and it goes over to AC volts. Well, that's it, folks. That wraps up our review of the XDM2041 digital multimeter. What do I think of it? I'm a little bit disappointed that it won't measure down past 5 microamps. The auto ranging in ohms mode is pretty slow. Its accuracy is fantastic, and I didn't find that problem that people on the internet found with it in the 50 megohm range, jumping around all over the place. It just didn't do that. In fact, as you saw, the signal was jumping around as much or even more, and it's a meter that costs 3 times the price of this one. I've taken down a list of things that I liked and what I didn't like, and the only things that I didn't like were the fact that it's got an RS-232 port instead of USB. I don't necessarily like having to install National Instruments Vista, but I have to do that for my Signet anyway. It seems that everybody's going that way. And the documentation really it's all over the place. So it could do a revamp on the documentation. Some of the things that I really liked about it, I like the fact it's got the fuse holder right there. Having to take apart your meter to replace the fuse is a bummer. So I like that. That was a real smart move. I like that it has 55,000 counts. That's great for a meter that costs well under $200 US. I like the form factor too, is the way my lab is laid out. I've got a shelf up at the top for all my instruments, and they have to stack up vertically from there. And this would fit in perfectly. I like that it has the 4-wire ohms. That's a nice feature. It's got a nice display on it, very easy to read. Continuity is nice and loud, so you don't have to be looking at the meter. You can hear that. It came with a serial cable. That's a nice touch. The ranges are excellent. It's got a full set of functions. It's really not lacking anything there. I like the dual display. I think the user interface is excellent. The way it's all laid out, I only had to look at the manual maybe once or twice to be able to figure out what I was doing. Very low learning curve on this. In continuity, I like that you can change the threshold. That's a really nice feature. It's got a good diode voltage, so it's 3.28 volts we measured. And I like that it boots really quickly. So, there's a whole list of things that I like about it. A very short list of things that I don't like about it. So in the end, can I recommend it? Yes, I can. All right, folks, I'm going to draw this to a close. I realize that this might be a slightly longer video than I normally do, but I just want to get this finished up in 2 videos rather than 3 or 4. Thank you very much for coming out. I hope you got something out of this. If you're trying to make a decision about something like this, I think this is in that price range, that sub $200 price range. This is a solid contender. And other than that, I'll see you in the next video, guys. Bye-bye.